Hi, we are going to start with the buck converter design, and for this video we are going to generate the simulation file of the LTspice circuit, and we want to work under very ideal conditions. So the first step is to obtain the duty cycle, the inductance and the capacitance that we need for the circuit, and to do that we are going to use the specifications that we set in the previous video. I'm not going to repeat them. We have this information, and we also have three equations that we explained in previous videos where we analyzed the buck converter under ideal conditions. Okay, that was the expression of the output voltage, the current ripple through the inductor, and the output voltage ripple. So with these expressions we can obtain duty cycle, inductance and capacitance. In the first case, or the first equation allows us to determine the duty cycle is 0.275. The second equation allows us to determine the inductance is more or less 7.9 microhenries. And the last equation allows us to determine the capacitance we need. So in this case is like 230 microfarads. Well, let's put this information in the circuit. So here we have the schematic that I have designed. Some comments. Here we have the input voltage, here we have the main switch, here we have the diode, the inductance, which is ideal, the capacitance, which is ideal, or the capacitor, and as the load we have the a resistance to model the load. So the resistance value can be obtained taking into account the output power and the output voltage. So basically we can use this expression, and here we know that this is 50 watts and VO is 3.3 volts. Okay, you manipulate the expression, you obtain the resistance of the resistor, and you get this value. More comments. I'm going to simulate the circuit during 2 milliseconds. The maximum time step is 1 nanosecond to have good resolution in the waveforms. And more things. I'm going to define 3 nodes of the circuit with a particular name. I will call this node in, I will call this node out, and this is the switching node. I do this in order to facilitate the interpretation of the results we are going to obtain. Otherwise you will get a random name with some numbers for the node, so it's difficult to see what you are evaluating. Well, next thing we need to explain is how we model the switch and the diode. I'm defining my own models. Okay, I will start with the switch. I define a model of the switch considering these parameters that I am including here. First of all, when the switch is on, I want a short circuit. So in LTspice we cannot put a perfect short circuit, so we have to put a very small resistance. Here we use 0.1 nano ohms. Similarly, when we want a switch that is off, we want an open circuit, so we have to put a very large resistance. In this case I put 100 mega ohms. And finally, this is the threshold voltage for the control signal. It means that if we put a voltage higher than 2.5, the switch is on. If the control signal is lower than 2.5, the switch is off. And well, basically this is the model that we use for the switch in order to have a scenario as ideal as possible. Regarding the diode, we have a very similar approach. In the case of the diode, when the diode is on, we also want a short circuit, so we say that the forward voltage is 0, but we have to put some resistance. So we put a very small resistance value. When we want an open circuit, we cannot put an infinite resistance, but we can put a very high value. Well, more things to comment, to mention I have here. Let's talk about how we control the switch. We have to put a control signal to say when we want a short circuit and when we want an open circuit. So let's see how we generate the control signal, taking into account that the threshold voltage is 2.5. So what we are going to do is to put a pulse voltage waveform, and we are going to define two parameters: duty cycle and switching frequency. I do this because we are going to put, not in this case, but in future cases, we are going to put those parameters in a lot of different places. So in this way, since we are going to change the values, it's easier if we do it in this way. How we define the control signal? So we are going to generate a pulse voltage waveform, and we are going to consider these parameters. This is the voltage value in low state. This is the voltage value in high state. So we are generating a voltage like this. This is 5 and this is 0. Time delay is not important. We can put 0. Rising time and falling time, ideally we want 0, but in LTspice if we put 0, we are going to have problems. So basically the rise time and the fall time is this. This is the rise time, and this is the fall time. Here we have 0, here we have 5, 0. So basically it's the amount of time that the control signal uses to change from low value to high value and vice versa. Okay, so ideally 0, but if we do this in LTspice we are going to have a problem. So we have to put a very small value. 0.01 nanos is okay in both cases. What is T-on? T-on is the amount of time the voltage signal is on high value. So this is T-on. And finally, this is T period. Okay, according to our target, T-on should be D times the switching period, and T period should be equal to the switching period. Okay, I'm working with the frequency instead of with the period. So what I do here is to put D over the frequency, and here I put 1 over the frequency. Okay, so with this we have the simulation file on LTspice considering a very ideal scenario. So in the future, in next video, we are going to see the results we obtained. So thank you for watching and see you soon.